Uh, so when I introduced the terminologies related to this course, I mentioned disturbance. And disturbance can be considered as either a small disturbance. I mean, what happened? Oh, so small disturbance basically means to study this disturbance, you can only you can use the linearized model. You don't have to use the original nonlinear model. Although nonlinear model is accurate, but when the disturbance is small enough, so what exactly happened is not important to your analysis. So even if you use simplified linearized model, you still can get the accurate result you want. And such disturbances can fall into a small disturbances. For large disturbances, you have to use an original nonlinear model or somehow reduce nonlinear model. And for large disturbances, you do need to define the location, type, and also any details of the disturbance, because any change in the location, the type, or the detail may cause inaccurate result. Okay, so today we're going to utilize those two concepts when we talk about the classification or definition of power system stability. Let's talk about power system stability. Power system is a nonlinear dynamical system. Okay, so when we say power system stability, we basically mean stability of a power system as nonlinear dynamical system. So you may wonder, why do we need to specifically define the stability of a power system? Because it's too complex. So we have to define some subcategories or classes, such as we can decide what model, what technique we can use. For instance, we can classify the disturbances into small and large. So for small, we can use linearized, simpler model. For large, we can use more complex model. But definitely, if you have very strong computational power, you can definitely use the same model, the most accurate model, but it can be very slow, very time consuming, okay? Let's assume this is the model of very accurate model of a power system. So as dynamical system, it has a lot of state variables. So state variable means which differentiable. So if you can calculate derivative and put on the left-hand side, that can be considered as state variable. For some variable, they're not differentiable. They cannot be the state variable. Okay. Some examples such as for some like control parameter, you allow any step change. When you do a step change, it is not differentiable at the changing point, so it's not state variable. The state variable really means the internal variables categorize the state of a dynamic system. Okay, because for any dynamic system, a change may not happen instantaneously. It has to be going through some dynamic process with certain time constant. So that time constant defines how quickly you can change such variables. So that's why each variable cannot change instantaneously, and its speed will depend on some function, like x dot, which means time variable of the time derivative of the x variable will be determined by the f function. Okay, so that speed cannot be infinite. So it will take some time to speed up or maybe slow down. Y is also state variable, but here I especially put epsilon multiplying the y. I just want to say that epsilon is a number much smaller than 1. The purpose is just to differentiate x from y, because epsilon is very small. Epsilon is somehow like an average time constant of all the variable falling into that y vector. Okay, and that time constant is much smaller than time constant of x. So we treat y as fast dynamic variable and x as slow dynamic variable. So examples for x will be anything like electromechanical dynamics, such as the rotor angle, frequency, speed, anything about the rotor. So it will take some time, right, for the rotor speed to change or angle to separate. Take a few seconds, okay? But there's some other variable which may be inside of the controller, like digital controller. The change can take microsecond or millisecond. So those can fall into y. So I just want to say this equation represents the accurate power system nonlinear model, but some variable will be slow, some variable will be fast. So this is the regional model with 2-time scale. You can use this model for any stability study for power system. So if you have a strong enough computer, so you can definitely use this model. Definitely, it may be very slow. So if we only focus on the slower dynamic, which means the electromechanical dynamics, anything involving the rotors of generator or any like dynamics of generator, it takes maybe several seconds or maybe a fraction of seconds to change. Then we can ignore the dynamics which are much faster, such as the electromagnetic dynamic, which indicate if you have short circuit, how the current and the voltage change instantaneously near the fault. Then we can simply let epsilon be 0, right? Because epsilon is much smaller than 1. So by doing this simplification, it doesn't change much on the result regarding X, but it definitely changed some dynamics of Y. But because dynamics of Y are not important to electromechanical dynamics, so we can just make this simplification. And we also keep in mind, so if we make both X dot and Y dot be 0, so we need to solve a number of algebra equations with F and Y, with F and G. So those solutions will indicate the equilibrium points of the system or operating condition of the system. So this is typically the model we are going to use for transient stability study. DAE just stands for differential algebra equation. So usually transient stability study use the differential algebra equation, not original detailed ordinary differential equation, ODE model. By using this DAE model, we can find the Lyapunov function for direct stability analysis, or we can do simulation. We can integrate this model starting from any initial state or some disturbance, so we can calculate the response of the system. And we can even identify a domain of attraction, which means once the state go inside of the domain, it will never exit without further disturbance. So system will be stable. Okay, so those are some issues, the transient stability problem concern. For instance, they just show the domain of attraction about the single machine infinite bias system. A single machine infinite bias system is just studying the transient stability about single synchronous generator versus the rest of the system, which is considered like infinite bias. So the system has a 2 equilibrium point, green one and red one. The green is a stable equilibrium point. Surrounding the green point, there's a like spiral, just indicate the trajectory. So if you start at any point in the space, it will follow that trajectory until it reaches the green one, the stable equilibrium. But if you start from the red one, it will become unstable. The red one will indicate the boundary of domain of attraction. Okay, so such figures in the phase domain can be studied using this DAE model. You don't have to go to that ODE model. So this one can give you accurate enough result to study transient stability. We will discuss such figures in the session of transient stability. So this is about transient stability. Okay, that's one category of power system stability. There are also some other problems, and we don't really worry about the state going outside of domain of attraction. So we already know. So for this, for a number of disturbances added to the system, it will always behave near the equilibrium point. It never move too far away. Okay. So for instance, if I can draw something here. So if we know for some disturbances which are small enough, and the system dynamic will be stay inside a very small neighborhood of the stable equilibrium. Okay, so then we don't have to use that complex model. We can maybe simplify the model. One thing you can do is instead of studying the X and Y as the state variable or the non-state variable, we can study delta S and delta Y relative to the equilibrium point. Okay, we already know the S equilibrium, Y equilibrium will be the operating condition. Okay, so then we can linearize the DAE model by using Jacobian matrix about the both F and G, and we take the value at the equilibrium point. Then each partial derivative here will become just a constant matrix or constant number. The nice thing we can do is using the second equation, which is a linear equation, we can solve Y. By solving Y, we can plug in the solution into the first equation of Y. Then we get rid of Y. So we can easily get this linear model only about X. So here it's only, there's no Y. Y have been eliminated, but definitely Y will be will influence A. A is basically the final the Jacobian matrix of the system, only about the state variable. And this is a linear system describing how the state variable change around the equilibrium point. For this system, we can utilize some linear system technique to study stability. So one thing we can do is you can find all the eigenvalues, right? So if all the eigenvalues on the left-hand side of the complex plane, on the left-hand side of the imaginary axis, the system will be stable. But if there's any eigenvalue on the imaginary axis or on the right-hand side imaginary axis, the system will be marginally unstable or unstable. Okay. So that is a model utilized by small signal stability analysis or small disturbance analysis. So for this this is second category of stability problem, small signal stability. So such problem concern the oscillation modes and the damping. So if the system oscillates, what frequencies and what dampings the oscillation has. And if the damping is not large enough, or if the damping is negative, which means it's a growing oscillation, then we need to take some control. But if it's decaying oscillation, but damping is too small, it takes a very long time to go back to the equilibrium, we need to increase the damping. So any damping control, damping estimation, or damping monitoring, or oscillation monitoring fall into this category of stability problem. So the technique will be related to the eigenanalysis using the eigenvalues. Eigenvalue will tell the stability. Okay, for instance, for a single machine InfiniBus system, there's only two eigenvalues, a conjugate pair of eigenvalues. If it's both on the left-hand side, which means it has positive damping, it will decay even it's oscillating. And you can read about the frequency and damping ratio from the eigenvalues. If it's more complex system, there will be many eigenvalues. Okay, so each eigenvalue will have eigenvector. Eigenvector indicate how each variable participate or behave or contribute to this mode, to this frequency. That will bring some concept such as mode shape, mode composition, and participation factor. But we'll cover all those indices in the small signal stability session. There are another stability problem. I don't worry about oscillation. Maybe the system doesn't oscillate at all, or even if it's oscillated, the damping is very large, it will quickly decay, maybe after one swing. Okay, but for such system, the equilibrium point can move all the time. Then for this case, let's ignore the dynamics. Let's assume both I star and the Y dot be 0. Then we'll get two algebraic equations. There's no dynamic at all. But we do need to consider the change of some parameters, such as the load. Then we can rewrite the equation in this form. Here, X is still the state variable, original state variable from the generator, for instance, and all controllers. And V will be the bus voltages we really consider. And S can be maybe loading of the system, like active load, reactive load. S here may be complex power. So we need to study this system. So you may ask, if we ignore all the dynamic, how come we still have stability problem? Because this is the third type of power system stability problem, which is called voltage stability. So even it's called voltage stability, but this problem can be studied based on purely algebraic equation. You don't have to consider state variable. But you do need to keep in mind the variable here, x and v and s, they have different meaning. S means there's a state variable of a regional system. V means something we really care. Like for this case, we want to have the voltage high enough, and S will be something changing the system equilibrium point. So to study the stability of this problem, we'll look at another domain. So here, like x is about the root angle, which is maybe one variable from x. So this is like one variable from x, okay? And y will be one variable from the v. So if we visualize the system trajectory here, we have a stable equilibrium and unstable equilibrium, which are same as this figure, right? But here we just add another dimension, v. V just indicate the voltage. Oh, there's actually, you can also add another dimension, which is s, which is the loading. So we visualize the system trajectory. For this simple system, it will have three dimensions, s, v, and s. And we're interested in how the s will change the distance between the two equilibrium. Okay, so when the s increase, the green dot and the red dot will get closer and closer. Finally, there's no green dot at all. The system become unstable. So it's impossible to keep the stability. So which is this one. This phenomenon is called bifurcation, or saddle node bifurcation. All right, so now I introduce three types of a power system stability problem, right? We start from transient stability, which can be studied based on the DAE model, differential algebraic equation model. That is a classic nonlinear stability problem. Okay, so you can use any technique like a Lyapunov function or power system time domain simulation or domain abstraction to study stability. The second problem is when the disturbance is small enough, and the system variable will stay closely near the equilibrium, the stable equilibrium point. We only use a linearized model, study the deviation from the equilibrium. That will be the problem about small signal stability. Okay, we can use eigenanalysis to find eigenvalue, eigenvector to study stability or control the system. And the third type is voltage stability. For this case, we ignore dynamics, but we study how the distance between stable equilibrium change against the unstable equilibrium. So under what condition the stable equilibrium point disappear. And this can be studied by another technique, which is called bifurcation analysis. So this one gives you a big picture about any power system stability, or at least for three classical power system stability problems. Any question? Okay, so I'm not sure every one of you will select the power system stability as your dissertation, but if you study involve any stability analysis, make sure you use the right model and the right technique. Okay. So now we can talk about the classification of power system stability. So I need to emphasize this sentence. The power system stability is essentially a single nonlinear system stability problem. The reason for us to define different categories and select some technique or simplified model because it's too complex. But if you work on small system, like if you work on microgrid, which only just have maybe a few generator, don't limit your method by the classification here, right? Here is merely just help you to simplify the stability problem for a very large scale power grid. So if your system is not large enough, just use the most accurate model and whatever technique you can use. So treating the power system stability as a single problem will be ideal, but in practice, due to the limited the computational power or the resources, we may have to narrow down the reasoning and also to simplify the model to make analysis easier. So the analysis of stability need to identify the key factors that can contribute to the instability. So if you know the key factor, you can somehow keep the modeling details regarding those factors. But for the other unimportant factor, you can somehow reduce the model. Okay, then they can speed up your analysis. So let's talk about the classification. There's a reference. This is actually a task force report by IEEE, and it later became a translation paper on IEEE translation power system, published 21 years ago, almost 21 years ago. This one defined the classification and the meanings of a different power system stability problem. It considers 3 dimensions to classify those problems. The first dimension is about the physical nature of the phenomena of the problem. Like if you first observe, or maybe the phenomena mainly reflected on the rod angle, frequency, or voltage, you can simply call it like rod angle stability, or frequency stability, or voltage stability, based on the physical the physical nature of the problem. The second dimension can be based on the size of disturbance, as we mentioned. It can be small, large. The difference between small and large is really depending on whether the linearized model can meet all your requirements of analysis. Okay, so if you can use the linear model to do the study and compare the result against the result from the regional model, they're basically the same. Or even they have some difference, but different not important at all for you to design the controller. Then this problem is falling into a small disturbance problem, not a large disturbance problem. The third dimension is about the devices, the process, and also the time span. Because there's some stability problem, if it happen, usually take a long time to finish. But some stability problem can happen quickly, in a few seconds. So based on the range of time period, we can categorize the problem into transient or short-term problem. By transient, usually we mean within 10 seconds. Okay, the major phenomena can be observed within the first 10 seconds after the disturbance. For midterm problem, which means take 10 seconds or several minutes to evolve and finally cause maybe big problem. Like for instance, like voltage stability. Voltage stability involves the change of the load, because load takes some time to change. To make the stable and unstable equilibrium point to be closer, finally merge. That does take some time for some systems. So usually that can fall into the midterm problem. But it doesn't mean the voltage stability has to be midterm. It can be short term. If you have something switch, that can make the stable and unstable equilibrium point merge quickly, like just in 1 second. So let's still go back to the transient. This just gave you a third dimension to clarify those problems. And the last one will be long term. There's some other problem it take even maybe several minutes or tens of minutes to finish. Okay, so we mentioned in the first dimension, there's the angle, frequency, voltage. Second dimension, we have a small and large. And third, we have a short term, mid-term, and long term. So which means for all the combinations, all the possibility, we will have a 3 times 2 times 3. 18 types of different stability problem. But some of the problem in such combination may not be real problem. which means they don't exist in a well-designed power system, or engineer already designed the system, power system to avoid such problem. So finally, there are only a very few stability problems we need to focus on. So let's show. If we start from power system stability, by first dimension, we have a rod angle stability, frequency stability, and voltage stability. Those three large categories. And by disturbance size, we have a small disturbance angle stability, large disturbance angle stability basically means transient stability. The transient stability typically means large disturbance rod angle stability, or large disturbance angle stability. They basically mean the same thing. And voltage, you have a large disturbance voltage stability or small disturbance voltage stability. And for the based on the range of the time period, for the rod angle stability, because that take a very little time to either be stabilized or damage the generator. So it doesn't make much sense to simulate the rotor take a long time to lose stability. So that won't happen in real world. So we only focus on the small term, which is transient stability. So for transient stability or rod angle stability, we can typically study in maybe 10 seconds or 20, or maybe tenths of a second. It won't be too long. And for voltage stability, there will be some small term or long term, depend on what is the cause of the voltage stability. If it's caused by slowly changing the load, it takes 10 minutes, a couple hours to push the system to the stability boundary, so that will fall into the long-term problem. If it's caused by a contingency, if you lose a generator or switch a line, and that suddenly make a stable equilibrium disappear, so that fall into the short term. And finally, for the frequency stability, for well-designed power system, the frequency stability is not a big concern anymore. It may become concern under like cascading failure. If the system become weaker and weaker, finally, the system is unable to operate around maybe the synchronous frequency. The frequency will collapse. But such phenomenon is very rare in normal condition. Okay, so so we can just ignore like a small size or large size disturbance, and if you want, you can study how the frequency change in short term or long term. Okay, so this is the classification recommended by IEEE task force. And even today, we still follow. So if you want to study one type of stability problem, please be clear about which category you are focused on, right? You don't create U category unless it is some new phenomenon, right? For instance, there will be a lot of renewable being integrated to the system. There could be some new phenomenon that cannot fall into any of the category. So that becomes a new stability problem. You can define that problem. But if you study just conventional generation about how the rotor will become unstable for a single generator or how the voltage decline, just comply with the definition here. So the bottom of the slide gives you three examples of some problem. The first one indicates the system is oscillating. There's a sustained power system oscillation. So typically that falls into the small disturbance angle stability. So that can be studied using a linear system, linearized model of the power system. And the middle figure indicates 3 generators are speeding up and separate from rest of system. So that is a typical out of step phenomenon that fall into the transient stability problem. Okay, so this one, if you want to find out how this one happened, you have to use the technique for transient stability analysis. And the last one is from a real power blackout, which happened in 1996 in July, on July 2nd in the Western connection. So this indicates the voltage at some power plant, right? So you see at the end, the voltage quickly dropped to a very low value. The entire system collapsed and the blackout followed. But before the last, if you can, this is too small, but the last collapse happened actually within several several seconds. But before that collapse, the voltage still stay closely around the nominal voltage, because this is about the substation around 220 or 230. So you see the voltage at least above 200 kV. So it's not too bad. You see some variation of voltage, but the collapse is not clearly predicted from the trend of system. So when the voltage instability happens, it's not like linear process to decline the voltage. It can happen suddenly. That is caused by the stable equilibrium and unstable equilibrium they merge, and the stable equilibrium disappear, and system just collapse. Okay. So those are three examples of three types of the stability problem. So in this course, we're going to focus on those red boxes. Okay, we'll have three sections. One section about the small disturbance angle stability or small signal stability. One section about transient stability, and one section about voltage stability, including both small disturbance and large disturbance. Any question? This slide just give you some idea on how the frequency can change. And we use the live figure before. We just indicate for any disturbance, the frequency of a generator or frequency of system will experience three stages. The first stage is like at point A, at the disturbance, the time instant of the disturbance, because the generator has governor to regulate the speed, but the governor is not like ready to regulate frequency anytime. Usually there's some dead band. Dead band means if the frequency vary too small, I don't have to use governor, because if governor takes some control, it will adjust the valve opening of the turbine. That will influence the power of input to the generator. So I don't have to make the turbine or valve control be too sensitive. So I set up this governor. Usually governor dead band will have about 30 milliseconds. You see it will react at 59.79 hertz. So for this case, that is a 30 millihertz dead band. Okay, within that dead band, and the frequency will drop following this slope. The slope is mainly depend on the total inertia of the system. So if the system inertia is large, and this slope will be small, but if the inertia is too small, the frequency can drop very fast. Then beyond this dead band, the governor will try to bring the frequency back, but it takes some time. So usually after several seconds, for the first example is around maybe 4 seconds. In the second example is typically it can take 5 seconds to reach the minimal frequency. And if the minimal frequency is too low, that will trigger some protection, will trip this unit. So we don't want that one to be too low. But if governor control is effective, it will bring the frequency back, but it cannot bring the frequency back to 60 hertz. It will take a third stage, which is automatic generation control, to bring the frequency back, finally to 60 hertz. Because we have so many defense of the frequency drop, including the inertia and the primary frequency control by the governor and also AGC by the region. So it's not easy to have a frequency collapse. So you have so many control to try to bring the frequency back to normal value. So that is one reason we don't emphasize too much about frequency instability. Theoretically speaking, a power system may have frequency instability if you don't have governor, you don't have AGC, and your inertia is too small, the frequency may collapse. But in a real world, the frequency instability is not that critical anymore. Okay, so next few slides, we just quickly go through each category of stability problem. The first one is rod angle stability. So for rod angle stability, this includes both the small signal stability and the transient stability. For this terminology, it's okay, you call it rod angle stability or angle stability or angular stability, I think anyone will be fine. Anybody understand? You are talking about generator, the stability of generators. If a power system can have all the synchronous machines operating in synchronism, which means their frequency are very close, their angles don't separate too much. Usually it will satisfy the rod angle stability. But after disturbance, the system may lose the stability. If it's a large disturbance, system may just go outside of domain of traction, and some generator will fly away, become out of step. If it's small disturbance, that may cause a generator oscillating all the time, right? It takes a long time to be damped. So that will cause some small signal stability problem. So the phenomenon of instability is typically the increasing rod angle swings of some generator leading their loss of synchronism with others. Like for instance, for this power system, this is part of the NPCC, the Northeast Power Coordinating Council system. It may have several regions, and the generator tend to become coherent group within each region. Okay, and if you have disturbance that can speed up maybe one region of generator and to become out of step against the rest of the system, or if you may have a single generator flying away. So those all called out of step problem, or they're all transient instability. So for the research paper talking about the rod angle stability, some paper might use this term like dynamic stability. Dynamic stability, this term is not wrong. It came from the control theory from any other like field about power system, not power system, about nonlinear dynamics or linear dynamics. The dynamics, the first word dynamic just try to emphasize this is about dynamical system. But this term is not very accurate for power system because we already defined different categories of problem, right? So we need to avoid using this terminology in research paper. If you find those maybe all the literatures that utilize like dynamic stability, if it's published on like North American journals, usually it means small signal stability. But if it published on some European journal, it typically means transient stability. So which means it can cause some confusion. So both Sigrid and IEEE don't recommend using this terminology anymore. Okay, so if you study general nonlinear dynamic system is fine. You can call it dynamic stability or dynamic instability. But for power system, just use the terminologies we define. Okay, or just go to that task force paper about classification. The rotor angle stability depends on the ability to maintain or restore the equilibrium between the mechanical torque and electric torque. Mechanical torque is actually it comes from the force added by the steam turbine, right? You have if it is a steam turbine generator and the steam will turn with high pressure steam, high temperature, high pressure steam will turn the turbine and will turn the rotor, okay, to generate mechanical torque as the input of the rotor. And because the rotor will induce electric field, the electric field will support the electric load of the power system. That will become the electric torque. So usually the two torques need to be equal. That based on the Newton's law, Newton's second law. So if the mechanical torque is higher than electric torque, you're going to generate accelerating torque. Accelerating torque will accelerate the rotor. The speed will increase. If the mechanical torque is less, the speed will decrease. So this is pretty much just the second law of Newton's theory. Okay, so for a simple power system, such as it's a single generator powering a single load. For instance, you can buy a diesel generator and place in your house, right? When there's a power outage, you can use that diesel generator to generate electricity to power your entire house. For such a simple power system, it doesn't have a rotor angle stability problem at all. Because the condition of rotor angle stability problem is when both sides have rotating mass. So one side could be generator, the other could be motor. Or maybe two sides, both are generator, but one generator is operating as a motor. Okay. So the rotor angle stability only become concern for such systems. So typically we only study any power system with at least two generators, or at least two synchronous machines. Maybe one is generator, the other is a load. Or maybe both are generator together powering some load. But those two generators need to stay closely at maybe around the synchronous frequency. Because only when you have two generators, accelerating any single generator can become a concern, right? If you only have a single generator, you can accelerate this one or decelerate this generator. It doesn't matter at all. It still generates electricity. The thing about if you have a diesel generator powering your entire house, you can, maybe the diesel generator has been advanced enough, you can program the diesel generator to generate 60 Hertz electricity. That 60 Hertz electricity is purely because all your appliance is designed for 60 Hertz. But if it's also okay to operate at 50 Hertz or maybe 70 Hertz or whatever, it's actually the frequency doesn't really matter. You can program that diesel generator from 60 to 50 or whatever number, as long as it doesn't damage your appliance. Okay, so which means if there's any imbalance between the mechanical torque of your diesel generator and the electric torque, which is the load of your house, the generator will speed up or maybe slow down. The frequency will change, but it doesn't lose stability as long as all your load, all your device can still be powered. There's no like out of step, right? Because there's only just one generator. There's no second generator. This is the first case. So even the first case, you still have single generator, but that one it's not synchronized with anyone. It just operates on its own. So the frequency can change, but we don't have many concerns about the rotor angle stability for such system. It's just too simple. But second type of system, you use a generator to power another synchronous motor as a load, which could be like from a large manufacturer. Then the synchronization will be important. For such system, even you only have a single generator connected to a single load as a motor, you still have a rotor angle stability. But the rotor angle stability here will be about the separation between the angles of this generator and motor. So if that angle can stay within very within certain limit, so the system is stable. If it's keep increasing and maybe generator flying away, or maybe the rotor just slow down, the motor slow down, then the system may become unstable. So for instance, if you read some research paper, they typically just use a like single machine infinity bus system. Single machine infinity bus system is not a single machine power system. Okay, that single machine is the first generator, but the infinity bus is another generator. Okay, it's just the equivalent of another generator. And but there's someone when they use single machine infinity bus system, they usually just omit the infinity bus, those two words, just call it a single machine system. It's wrong. I strongly suggest everyone not using not say single machine system. There's no such single machine power system. Okay, if you mean the first one, you use a generator to just power a resistive load. Okay, to start stability, you need to have at least two machines, two synchronous machines. Voltage stability refers to the ability our power system to maintain the steady voltage at all buses, especially after some disturbance. Okay. It can be studied by this curve, which we call the PV curve. X is the power transferred to the load through the network, and Y is the voltage at the load. Okay, so when the power is small, the voltage can be high, but when power increase, the voltage will decline following this curve, and then it can reach to this knee point or nose point or critical point. And beyond that one, the voltage quickly decline. This is exactly what happened in that 1996 blackout. We can use such a tool, PV curve, to study the voltage stability problem. There's another term which is voltage collapse. Voltage collapse typically just consider same as voltage instability, but the collapse just emphasize the phenomena. So before the collapse happened, the voltage seemed to be normal, close to normal, but suddenly the voltage become abnormal and voltage become very low. That's why we call it a collapse. So this is the typical phenomenon of a voltage collapse. And before the collapse, and the voltage stay close to the nominal value, but the collapse can happen quickly. So that is really because of the system past the critical point. The critical point is where the stable equilibrium and the unstable equilibrium merge. Okay. Because if you draw a vertical line, because x-axis is about the power, so if you draw a vertical line which indicates the load level, so if right now the loading level is around 2000, that will be this vertical line. The vertical line will intersect with the PV curve by 2 points. So it's a top point and lower point. The top point will be the stable equilibrium, and the bottom one will be the unstable equilibrium. So when the load increase, right? So finally, when this line becomes tangent to the PV curve, the 2 points will merge, and there's no stable equilibrium anymore. So that's how the voltage collapse happened. Yeah, this just quickly give you an introduction about this problem, but we have the whole section to discuss this problem. A very important question will be how to differentiate the rod angle stability from voltage stability. Okay, so here I gave you two typical examples which are typical example to study the two problems respectively. The first one is a small generator connected to a large system. So this is basically just single machine InfiniBus system. The large power system can be modeled by InfiniBus, and a single machine will be that small generator. So when the generator has a long path to connect to the large power system, and if anything, if there's anything happening on the path, that will reduce the power from the generator to the system. Okay, so the generator will speed up. So if you have short circuit on the path, and your turbine still send the mechanical torque or mechanical power to the rotor, but the electric power cannot be delivered along the path, then the rotor will speed up. So that's a typical rotor angle instability. A second figure is a typical case for voltage instability. So you have a large system connected to a load area. And for this load area, it doesn't have enough voltage controller. It only just have load. Okay, it may have some load controller, but it will not active load controller, power voltage controller. So we'll discuss what active voltage controller mean, okay, later in that session. But for this case, the power sent to the load area and the voltage measured at the terminal of the area, you can draw that PV curve. So this is P, this is V. Right. So when the load increases and the system reaches the nose point, and the voltage collapse will happen. So those two are typical scenarios of the rotor angle stability and voltage stability problems. But in real world, most of stability problems are not like may not be like either one, right? They can be a mix. They can be a very complex system. Then how do we differentiate rotor angle stability from voltage stability? So in reality, both type of instability may happen together. Okay, for instance, there's one scenario. So as the rotor angle between two group of generator approach 180 degree, so the loss of synchronism happen. So when the two groups are separated by 180 degree, it's very hard to bring them back. Actually, one group will separate from the rest of the group. That's a typical out of step scenario. But if you don't have a sensor, or which actually a physical memory unit to measure the angle, real-time angle for both groups, you only have some sensor on the path connecting one group generator with the second group. For instance, if you only have a monitor here, you can only measure the voltage and current. So what you can see is the voltage quickly drop to 0. But that is not because of voltage instability. Okay. This is actually the principle of out-of-step protection. Out-of-step protection is not out-of-step protection has been there for a long time before you have a GPS synchronized like a single phaser to measure the angle. They basically just measure the voltage at a middle point of a transmission path. So if that voltage drop to 0 and it can largely oscillate between 0 and maybe a high value, that is a typical out-of-step phenomenon. Okay. So this may be a tricky scenario. You may misclassify the problem as a voltage instability, but actually it's caused by the separation of angle. The second phenomenon is such as the outages caused by voltage collapse or from the operating conditions that violate generator field current limit that can cause loss of a synchronism of some generator. So what they mean is, for the second case, if you have a small generator, if the system reaches the nose point to cause voltage collapse, very likely that small generator will become transient unstable. Okay, that generator will lose stability. Yeah, you can see, okay, that generator has some transient stability problem or transient instability, but the root cause is not really that generator speed up flying away. It's really because of, for this entire load area, it has voltage collapse. So voltage collapse is actually the root cause of this stability problem. So this is another tricky scenario. So if you don't have the big picture about the entire system, you only just measure a local generator, you can misclassify this problem as like transient instability. Okay. So those are just some scenario that remind us the real world phenomena can be very complex. That can mix the rotor angle stability and voltage stability. So when we go to the two different stability problems, we will have more discussion about how to identify or how to analyze the root cause of each problem. But for now, you can just remember those two sentences. For the rotor angle instability, it occurs when the angle speed of a rotor does not go back to a stable equilibrium under disturbance. Basically means the system state go outside of the domain of traction of the stable equilibrium. So this can be considered rotor angle instability or transient instability. But for voltage instability, that occurs when the stable equilibrium itself disappears or change due to a switch in the system or load increase. So this is mainly caused by bifurcation. The stable equilibrium and unstable equilibrium, they have to merge or stay too close with each other. Okay, any question? All right, so in 2020, so IEEE developed another report, just make some revision or modification of that old classification paper. So that one, the first one was published back to 2004, and 16 years later, they they somehow just add more category to the classification. So there are a number of concerns. Because the future system has a lot of renewable integrated to the system. And the renewables, usually they don't have inertia. They either have no inertia or their inertia don't have a lot to support the system frequency. For instance, if you have like a type 4 wind turbine generator, okay? So even the wind turbine has inertia, but the power it delivers through the power electronics. Then the inertia doesn't help to support the frequency, or the turbine generator, the rotor doesn't operate at the signal speed. And for the solar farm, it doesn't have inertia, okay? And also another concern is like when the coal-fired power plant retire, and there's some smaller gas turbine generator will be installed to take their place. So the trend of the system will have a decreasing inertia for the entire power grid, and there are more and more fast dynamic. So if we try to present all possible dynamics, so that paper just gave you this chart that indicate all dynamics. So, for instance, the first one is a lightning propagation, and the next one will be a switching surge and inverter-based controls, stator transient and subsynchronous resonance, a rod angle dynamics. The first three actually fall into the time frame lower than 1 millisecond. Okay, from microsecond to millisecond. Then the next several are such as stator transient and subsynchronous resonance, rod angle dynamics, governor and low frequency control. Those three fall into the transient dynamic from millisecond to maybe 10 seconds or tenths of second. And the next several like voltage control or boiler dynamics, so that can last even longer time. The classification we have introduced cannot cover everything here. So we have to add something to cover, for instance, especially the fast dynamics. So then they propose this new classification. So you see that the right three branches are same, exactly same as the old one. They add the two new branches. The first one is called resonance stability. The second is called converter-driven stability. The resonance stability there are two types. One is electrical, the other is torsional. Torsional electrical, their difference is mainly depend on whether the mechanical part of the generator participate in the resonance. Okay, if it's only electric resonance, it will be fall into the electrical resonance. So does anyone know what resonance mean? What does a resonance mean? But why do we not call them oscillation? We call them resonance. So what is the simplest example you can think of about resonance? Yeah, LC circuit. So under what condition the LC circuit will have resonance? LC circuit does not necessarily have a resonance, but it may have resonance. Under what condition? Yeah, when the right. So if the LC circuit has some resistance, right? The resistance is large enough, usually there's no resonance. Okay, so when there's no resistance, LC will become a resonating circuit, and the frequency will caused by resonance. So that gives you an idea on how the oscillation is generated. It can be generated by resonance. But in order to generate that resonance, L and C will resonate. So if we assume the frequency, so if you calculate for the LC circuit, if you ignore the resistance, you calculate the impedance, or maybe the inductive reactance or the capacitive reactance, they just cancel each other. Okay. So for such circuit, if you solve eigenvalue, we have a pair of eigenvalue, conjugate eigenvalue. So it's 1 omega j and another negative, maybe negative omega j. So they just cancel each other. So which means for any resonating system, you need to have 2 eigenvalues, they just cancel each other, right? That's a simplest resonance. That's maybe called 0th order resonance or maybe 1st order 1 resonance. But for more complex circuit, you may have 1 eigenvalue, a second eigenvalue, and third eigenvalue, they just added together. Like for instance, lambda 1 plus lambda 2 equals lambda 3, which means lambda 1 plus lambda 2 will add energy to the third one. So they will be resonating. And you can have more eigenvalue resonating. So which means for such resonance stability, you need to have maybe 2 part of system. They just have a very simple relationship, such as the oscillation of one part will add it to another part. They have a reaction. So it's just like the oscillating energy, just like a ball pass from one to another, and they just bounce back and forth between the 2 players. That is called the resonance. But for oscillation, it doesn't need to have such relationship. As long as the system has complex eigenvalue, not all real eigenvalue, and it will be oscillation. But the real part of eigenvalue shows a damping. If the real part is very large and the oscillation doesn't last long, but they still have oscillation. Okay, so the oscillation only need to have eigenvalue which is not real. There will be oscillation. But resonance means a number of eigenvalue they need to meet a very simple equation. So we'll talk about maybe later when we go to the power system oscillation. So they put any phenomena that involve a resonance, especially at the subsynchronous frequency range. SSR stands for subsynchronous resonance. So if it involves mechanical parts, typically the frequency is low. They call it low frequency subsynchronous resonance. If it involves purely electric part, for instance, you have IBR, which operate at a certain frequency, and you also have like transmission, like series capacitor. So series capacitor will resonate with your IBR, inverter-based resource, and that can cause high frequency subsynchronous resonance. For the second branch, converter-driven stability, it may not have a resonance, but it does introduce some high frequency oscillation. So the oscillation is caused not by a single generator, it's caused by the inverter control. Okay, so if by poorly designed controller for the inverter. So if the oscillation is less than 10 Hertz, it's called a slow interaction. If it's higher than 10 Hertz, it's called a fast interaction. Okay, so if you know which part is resonating with which it is resonance, it can fall into the first branch. Otherwise, it's purely just a fast oscillation involving inverter, converter. It need to fall into the second branch. And the rest of system is about the generator, single generator, about the bus, the load buses, and about the generator frequencies. We still can use the other 3 categories to do the study. Okay, so this is my last slide. So on Thursday, we're going to talk about the generator modeling, the next session.